So here are two easy Ohm's law questions. A 12-volt battery is able to produce 2 amps of current within a certain circuit. What is the resistance in this circuit? Well, first off, we need to know Ohm's law. And Ohm's law says that the voltage is equal to the current times the resistance. And so you can think about this as the voltage is what is going to, the potential difference is when you put a charge in there, that's going to tell it how much energy overall it has. But again, it does depend on how much charge is there. It's not the energy that the circuit has. It's the potential that given a certain amount of charge that you can have, that there will be that much energy around. Current is the flow of this charge. In the case of a circuit, it's electrons. And then the resistance, this concept is one where it's defined by Ohm's law as V over I, or that ratio of, well, what is the potential difference from your battery that you can create here, and then what is the actual flow of electrons. When you take that ratio, you get your resistance. But physically speaking, you would think of resistance as a slowing down or damming up of the current flow, and so the current will be less if there's a lot of resistance, given the same potential difference. But if the resistance is lower, then there can be more current flow, and vice versa. So we want to know then what is the resistance in the circuit. We've already rearranged this by dividing out the I. We get this, and again, this is somewhat a definition of resistance based on Ohm's law. And so we can put in these numbers of 12 volts divided by 2 amps, and we get a new unit. Volts divided by amps here gives us 6.0 ohms, which is Ohm's law. This is the Greek symbol omega, sort of sounds like ohm, so we use that as the symbol. So when you see this, a bigger number in ohms means resistance, and so the more resistance means the more that you're going to dam up this this current, and it again is related to how much the potential difference is. You can think of this like, again, as a strong gravity field on a high cliff. That'd be lots of potential energy, or lots of work available, or this can be something smaller, a low field with, in terms of the analogy to potential energy in gravity. This is again the combination of gravitational acceleration and height sort of together is the analogy for electric circuits and the electric field. But very similar when you go back to the definition of how we calculate the electric field from Coulomb's law, and we get that out. So now we want to know if we have a 3 ohm resistor that's attached to a 12 volt battery by 2 wires. So let me draw that for a second here. We often draw a battery like so, and then we would say we have a resistor in there. There's the symbol for resistor. It sort of just is a squiggly line. And then we go back to the battery here. This would be the circuit that we have here. This would be a 3 ohm resistor. Here's wire number 1, attach it to one side. Here's wire number 2, back to the battery. And then we have that 3 ohm resistor in there. And that could be, anything. You could have a circuit like this where this is your battery and this is a light bulb, or anything else. So we want to know what's the current. What's the current going to be flowing through here? It's going to go from, current flows from positive to negative, although that's not really true physically speaking. The electrons do go from negative to positive, but we'll blame Ben Franklin for that. Luckily, it makes no difference in terms of the calculation. So here we know that we have a resistance of 3 ohms, and we know we have a voltage, a potential of 12 volts between the two, and then we have this between 2 wires, so 12 volts back to 0 here, and we want to know the current, and so we take Ohm's law, we divide out the R on both sides, and we're left with I is V over R, so very simple formula. So the current will be 12 volts divided by that 3 ohms. I just added a 0 there, which I didn't have before. And that gives us then 4 amps of current, which is a lot of current, by the way. But for these simple examples, it's nice to use some simple numbers to see how the formula itself works. So Ohm's law is a very basic part of introductory electricity and magnetism. So make sure you can use that formula, rearrange it for all three, V, I, or R, and it's going to come in very handy in our next topic when we're doing Kirchhoff's laws and solving for all kinds of stuff inside a circuit.